Um, we've been talking a lot about the potential for mass spectrometry as a powerful tool in radionuclide measurements. And in a strange sort of way, I'm going to be talking about radionuclide measurements, but use of mass spectrometry in a very different way, essentially using the capability of very excellent repeatability or precision to actually make precise or relatively precise validation of mass measurements, of a difficult mass measurement. In this case, I'm talking about mass measurements of dispensed solutions, aqueous solutions 1 to 5 milligrams, which it turns out are very difficult to measure because it's essentially evaporating while you're trying to get the mass of that solution. So even with very sensitive 6-place balances or ultra micro balances, you're essentially watching your sample disappear while you're trying to get the mass of it. This talk is going to be about using mass spectrometry for maybe getting around that problem. So the driver for this is that at NIST, we're working on developing a microcalorimetry measurement technique for activity, and specifically at NIST, we're looking to do massic activity measurements, essentially the activity per gram solution, per gram of material. And we want to use these transition edge sensor microcalorimeters because they have nearly 100% efficiency for something like alpha decays, and they have the kind of resolution that allows you, even for alpha decays, to clearly distinguish between something like a 239 and a 240 plutonium decay. The figure on the right of this slide that I'm showing you is some measurement data from a project that was done at Los Alamos National Laboratory in collaboration with some folks from NIST Boulder, where they actually did this. They used these transition edge sensors to clearly measure the ratio of 240 to 239 alpha decays using these sensors. But one issue with these sensors is that because you're essentially making your measurements at near absolute zero, 100 millikelvin, you tend to have very small measurement apparatus that you're working with, something on the order of square millimeters of surface to work with for putting your sample on, something that's embedded in a gold foil, for instance. So as a result, to make your samples and to have quantitative measurements of something like massive activity, you need to have to be able to dispense something on the order of 1 to 5 microliters, but know the mass of that dispensed solution with an uncertainty of like 0.1%, and that's expanded. So if you look on the lower left of this slide, this sort of explains what we're trying to do here. You've got some stock solution. You want to make something like this microcalorimetry measurement, and we have some methods for dispensing these solutions quantitatively using a glass microcapillary or even an inkjet dispenser. We can do this. Unfortunately, both of these require either compensating for evaporation while your measurement or a sort of a bracketing calibration for your inkjet dispenser. And when we were looking at this, we decided we needed a way of independently verifying that our weighing methods were working, because we can't just use a check weight or something like that, because we have to do these compensate for these evaporations. So toward that end, we came up with the idea of using isotope dilution mass spectrometry. Not so much to get at an amount of an element or an isotopic ratio, but to get at a mass. Now, I think most people here are familiar with isotope dilution in the broad sense, where you're trying to get an amount of material based on adding a known amount of spike and measuring isotopic ratios of the sample spike and the mixture. Well, with some simple algebra, you can sort of see that you can measure a mass of an unknown if you know the concentration of an element in both the sample and spike and the mass of one of the components. So the question is how do you get the kind of precision you need for what we're trying to do? And again, we're shooting for an expanded uncertainty of 0.1%. Well, if you need to know the concentration of both your sample and your spike, for lack of a better term, better than 0.1%, and then also be able to measure your isotopic ratios with an uncertainty of better than 0.1%, that's a very difficult thing to do. Fortunately, since what we're really trying to do is compare, to essentially use the mass spectrometer to get at a mass, we can get around this problem by not necessarily knowing the absolute concentrations of these two materials. If you can determine the relative concentration or the relative molality, moles per gram solution of these two components of your IDMS, you don't necessarily need to know those absolute values. And that's pretty much what we've done in this case. I'll explain that a little bit more as we go on, but we could do a whole talk just on this issue. So by substituting a calibration for this ratio of the amount of material in, for instance, a spike in a sample, we can sort of input that into a classic IDMS equation. And now what we need to know to get this mass is the mass of one of your samples, the essentially the data that you use to do a calibration. And the way we chose to do this calibration is, although we were looking to measure, a few milligrams of solution, we could take a couple of starting materials and then use macroscopic aliquots and mix those. For instance, half a gram of your unknown material or your sample, for lack of a better term, and then 50 grams of your spike. Mix those together to get a ratio that you can measure easily on a mass spectrometer, and then essentially you can calibrate this I guess molar ratios, and that's so. There's another aspect of uncertainty that factors into this, and that's your ability to make precise mass spectrometry measurements. Well, let me back up for a second. In this calculation, as I mentioned, you've got these masses that go into the calculation, but you have these isotopic ratios that you have to measure. There's essentially 4 different materials or 4 different isotopic ratio measurements of materials, but they're all the same ratio, the same numerator and denominator isotope in the ratio. And as a result of that, there's a lot of, if you measure it on the same mass spectrometer, using the same measurement technique, the same mass bias correction, the same material for that mass bias correction, a lot of the uncertainties in that ratio sort of fall out for this particular case where you're trying to get at a mass. And to save time, I won't go into this in detail, but just mention that for a lot of isotope ratio measurements, the uncertainty in the isotopic composition of your calibrant can be a major contributor. Well, in this case, that uncertainty completely falls out of your calculation for getting at mass. And I actually, for this particular case, I sort of experimented with this to see that was the case. I'm going to get into this more, but to do this actual work, we used a mixture of a highly enriched 155 gadolinium and a highly enriched 158 gadolinium. And for mass bias correction, we used a natural gadolinium material and assumed IUPAC values for the 156-158 ratio, which is about 0.8241. Well, to test this, I took some of our real data and I just plugged in an arbitrarily different value by 2%, which for mass spectrometry is a big deal. And I would get out the exact same mass value. So essentially, the uncertainty on my mass bias correction didn't really factor into my measurement, provided I was consistent in how I measured everything. So to do these kinds of measurements, we also need to use the best equipment, essentially high resolution multi-collector ICP-MS. You could potentially do this on something like a multi-collector TIMS, but the ICP-MS has some advantages here. The big advantage is that we can get the kind of precision on the measurement of the kind of ratios we would use for ICP-MS, 1-to-1, between 1-to-1 and 1-to-100, with precisions of 0.01, 0.025% relative standard deviation for replicate measurements. I mean, that's the kind of precision we're looking for. We can also make these measurements on Faraday cups so that we have fairly stable measurement techniques, or fairly stable collectors, I should say, so that from when we're measuring these different ratios, we don't have a lot of drift or variability in our collector side of things. And also, we don't need much material. A few milliliters of something with less than in the part per billion range is enough material for us to make these measurements on an ICP. So very shortly, very briefly, this is what we did. As I mentioned, we made these enriched solutions with gadolinium 155 and 158, with the 158 as our quote unquote sample, our more concentrated material. And then we made a less concentrated sort of spike solution that we would be adding the quote unquote samples to. While for the samples, we ampulated this because we wanted a fixed concentration of that solution when we're using it. For the spike samples, what we did is we gravimetrically split these up, very carefully measured out a gram of solution into a bunch of sample containers. So we knew essentially the mass of our spike ahead of time. But we also made calibration mixes of these, where we randomly, or we selected ampules and took half a gram of solution from that and added it to, as I meant, between 40 and 50 grams of the other material. Well, we did the mass spectrometry on both the end members and the calibrants, and then we actually did the experiments where we dispensed small amounts of this 158 gadolinium into these larger amounts of the 155. We did 3 different measurements. One was just a pycnometer measurement. These are polypropylene ampules that have been stretched out into a capillary that in the radionuclide metrology uses this very frequently to get quantitative masses for the solutions dispensed. We did this as a control, and then we used the microcapillary method for some samples, and in 2 different stages we used an inkjet dispenser to dispense between 1 and 5 milligrams of solution. So moving on quickly, here's some results. Of course, we have our end member solutions, and we measured the isotopic compositions of these. And just to sort of mention, we had a 97% enriched 158 gadolinium and a 95% enriched 155 gadolinium. This is the information for the calibration mixtures we made. As I mentioned, to do the calibrations, we took about half a gram of one material and mixed it with 40 or 50 grams of the other. And as you can see from this chart, we got excellent repeatability for our calculation of the ratio of amount between these 2 solutions. And we even did some reverse IDMS with a natural gadolinium to test this. And the uncertainties on this test were kind of high, but it's consistent with what we observed. So here's some actual data. The way to read this chart is important. This chart is showing the relative difference from the isotope dilution calculated masses for these solutions for the 3 different methods for weighing these solutions, including the polyethylene pycnometers, the glass microcapillaries are the ones in the circular, and these diamonds are the inkjet dispense solutions. So not surprisingly, the pycnometer method and the IDMS agree, but the uncertainties for the pycnometer method are large just because it's meant for more macroscopic type measurements. The microcapillary measurements, we see two values here, and that has to do with two different ways of modeling corrections for evaporation that takes place while you're weighing. The good news is that these two methods give fairly similar, although somewhat systematically different values, and they're all consistent with what we get from the isotope dilution work. The exception here with this sample is one that we knew was a problem. When we actually made this sample, we could see that there was a problem with the weighing. And it's sort of good that in a strange way, it's good that the IDMS is sort of showing that this weighing issue actually did translate into our ability to make that measurement. The two inkjet methods shown here, the first set of samples, the inkjet was never optimized for making this mass measurement. It was actually, we were using a method that was actually developed to know how much of a dispensed solution made it onto a sample, when we're trying to measure how much of a solution was actually dispensed from the orifice. And so essentially evaporation that takes place was not accounted for in this method. In a second set, we actually tried to optimize the inkjet printer for the inkjet dispenser for the calibrations for potential evaporation. And we also changed some variables to see how big an issue the evaporation was. And for these samples where it was sort of optimized to get the best values, within uncertainties, we're clearly getting the values that we expected to get. When we sort of increase the amount of potential evaporation during our calibrations, we can see that we start to get these systematic biases in our measurement. So, essentially, that's the kind of information that we were getting using this technique. I just want to mention quickly the uncertainties for the mass spectrometry based or the IDMS based mass measurements are primarily associated with the repeatability of, or the precision of our mass spectrometry measurements, both for the calibration materials and for the unknown. There's also a variability for our multiple measurements of the calibration for the molar ratio of the two materials. So just to summarize, this technique that we're looking to develop at NIST, this microcalorimetry with transition edge sensors, is potentially a powerful method with nearly 100% efficiency and excellent energy resolution. But due to the physics of the method, we can't do relatively large samples where we're going to need to quantitatively dispense a couple microliters, a few milligrams of material to make these measurements. And we're working with various methods to be able to do this dispensing in a reliable way. But we needed to calibrate these methods, or not calibrate, but essentially validate that these methods are working, and possibly calibrate specifically for the inkjet system. What I described here was using IDMS in a pretty different way to validate these kinds of measurements. And essentially what we did here is leverage the ability to get very precise isotopic ratio measurements from modern multi-collector mass spectrometers to make these precise estimates of mass. And in this case, we were doing better than 0.1%. So I'm sorry if that was a little bit of drinking from a fire hose, but I didn't want to take too much time with this presentation. Thank you.